Today we're going to talk about friction, and I know that Mr. Smigowski covered some of this, but I would feel bad if I didn't cover it myself, because I, got to make sure I cover everything. So, and I have a couple of handouts here as well. I hope you guys have them out there. Little handout says the nature of friction. It's about a 2 or 3 page thing with some text on it. Well, when you're up till 2 in the morning because you had an energy drink at supper time, Nate, you could always read it, and it might help you go to sleep. Right? So I'm just thinking of you, man. As always. Okay, so basically what I've done is I've taken this series of this handout here, and I've created notes that go with it. So if at the end of my little discussion here, if you're not 100% convinced of something or you want to read a little bit more, then you've got the handout that goes with that. Alrighty, so yes, the nature of friction, and as I like to say, don't let it rub you the wrong way. Cole, you're wrapping that conversation with Mom up again? Okay, tell them that you're in physics and you can't be bothered. Tell him Mr. Bennett says go back to class and leave Cole alone. Okay, so we're going to calculate the coefficient of friction. We're going to solve problems on flat and inclined surfaces involving friction. You'll probably get a bit of a work period tomorrow because I've given you quite a bit of stuff to work on, kind of thing. So friction is let me just get rid of that. Friction is a force that resists motion. It involves objects that are in contact with each other. There must be contact. And it's always resisting motion. It's always opposite motion, right? If an object is, sliding this way, then which way is friction? The friction is this way, right? What if the object isn't moving, but it's trying to move? Like what if you're pushing something to the left? Does friction oppose that? Even if it doesn't move? Like if I push on the smartboard that's attached to the wall, right? It doesn't move, but I'm applying a force. Friction is pushing back, right? So it's not opposite motion, it resists motion. It's the opposite direction to any motion that might exist. An object deforms a surface and vice versa. There's actually some controversy about what causes friction, like what's actually happening at the molecular level. Peter, are you listening here? Because it looks like you're texting, man. So some people believe that an object deforms a surface and vice versa, so they actually think that the tabletop actually goes like that, and that a plowing force is required to move the object over the deformation, so that it's actually pushing those molecules out of the way. Some people believe that. They think that irregularities interlock and offer resistance to movement. So they think that the surface of the block actually is rough, as is the surface of the table. Okay, that's the whole idea behind sandpaper, right? When you take that rough sandpaper and you rub it on the wood, smooths the wood, and what happens to the sandpaper as well? Gets smoothed off, right? Yeah, and you see that with shoes or tires or anything, kind of thing, right? They're not perfectly smooth, and they sort of get locked together. There are some beliefs that eventually, if surfaces are so smooth, they actually get so close together that there's an attraction between the molecules, and that actually increases friction when there's too much surface area in contact, right? Almost like a suction effect kind of thing as well. So, well, I mean, they're I mean, it's really not up to me to believe. I don't know. I'm just reading what I read in the textbook. I'm no scientist. This one kind of seems a little bit deforming the surface. It seems to be a little bit hard to believe. But if you think about it at a molecular level, those molecules are moving just minuscule amounts, right? So, I mean, I guess I believe it all, really, right? Okay, this you do need to know. Starting friction is the maximum frictional force between stationary objects. It's in there. If you want to be highlighting as you go, if you want to write it down, it's really up to you, kind of thing. I'm just summarizing what's in that reading. Okay, you're not going to find it just written down exactly like that. You might have to go searching and highlight it, or you can just jot it on the side. It's really up to you. So starting friction is the maximal friction force between stationary objects. Sliding friction is the frictional force between objects that are sliding with respect to each other. And I think, if I'm not mistaken, the next page, and if it's not, then I'll have to write it in. No, it's not there, okay? Starting friction is the maximum. Starting friction is always greater than or equal to sliding friction. We all know that if you're pushing an object across the floor, that once you get it going, it's a little bit easier, right? One reason is due to inertia, and the other is because starting friction is different than sliding friction. Okay? And they have different sort of coefficients as well. I think Mr. Smigalski has reminded you of the mu coefficient, right? That's a terrible way of writing it, what I just wrote there, so let me write that again. Right? It's actually a U with a tail on the front, right? So it's tail and then a U. So that would be mu S for static, mu S. And this one here, sliding friction is mu K for kinetic. Oh, my writing is so bad. Mu K. Did it again. Maybe, yeah. This one seems to get off really fast. I much prefer the Symposium. Anyways. Okay, so some properties of friction, some characteristics. They are on that handout. They're on the second page there. There's a whole page of them. Okay, so I've just summarized them. Friction acts parallel to the surfaces that are in contact and in the direction opposite to the motion of the object or to the net force tending to produce such motion. So that's what I was saying before. It's parallel to the surface and in direction opposite to the motion or to the net force trying to produce the motion, right? Box wants to move to the right. Friction is going to be to the left, right? Whether the box is moving or not. Friction depends on the nature of the materials in contact and the smoothness of their surfaces. You probably know there's different types of sandpaper, your 200 grit, your 400 grit, and actually the lower the number, the grittier it is, right? Am I right, Billy? Yeah. Okay. So the smoother the surface, more friction. So friction depends upon the nature of the materials and the smoothness of their surfaces, up to that point where you get that suction effect. Sliding friction is less than or equal to starting friction. I mentioned that already. Friction is practically independent of the area of contact. Common misconception that the greater the surface area, the more friction. Not exactly true. Friction is practically independent of the area of contact, right? Think about, people think that the skinny tires or the wide tires on drag cars or bikes, like the skinny ones on the bikes, has to do with friction. It has to do with pressure and heat, actually. So it's not really true. Starting or sliding friction is directly proportional to the force pressing the two surfaces together, which is a fancy way of saying the object's weight. The heavier something is, the more it's pushing down, and you get more and more friction. It doesn't change the frictional coefficient, and we're going to get into that as well. So you can read more about that on that handout. Here it is. This is the coefficient of friction. Come on, make that bigger. I say, oh, geez. There it is there, right? So the coefficient of sliding friction is the ratio of the force of sliding friction, FF, divided by the normal force, Fn, that we've been familiar with for a while now. You will notice that we have a force over a force. So what are the units? Newtons over newtons. And what happens when you have the same unit on top as the same unit on the bottom? They cancel out. And so what are the units on mu, Cole? No units. There are no units to mu. It is just a number that determines how much friction there is. Note that this is the friction force, and this is the coefficient. Did I spell it right? Coefficient. What changes the coefficient of friction? What things can you do to make the coefficient more? No, not the coefficient. Friction is the friction force. I probably should have. Starting or sliding friction force is dependent upon the weight. The only way to change the coefficient is to make the surfaces rougher or smoother. Okay? When you put on winter tires, you're changing the coefficient of friction because the rubber is softer and it's grippier, right? When the town crews throw sand on the streets, what are they doing? They're making the surface rougher, they're changing the coefficient. And when you change the coefficient, then that increases the friction force. Okay? Come on, what's next? Let's do an example question. Do you guys have the example questions? I don't think you guys do, right? I think they're attached for you guys out in Grandview and Winnipegosis. So example 1, I should have it. You got it out there? Okay. Yep, good. No Sam today. Oh, okay. So I'm going to have that test ready for you, Dick. Okay, and then Mustafa when you're ready too. Okay, so I got 3 examples for you here. Example number 1. An object has a mass of 10 kilograms, a force of 100 newtons applied to it. The coefficient of friction between the two surfaces is 0.25. Determine the object's acceleration. I should make a little note here that the mu value, let's just go back to here. This value for mu is usually less than 1. Did Mr. Smigalski tell you that? You just know that? Usually less than 1. There are some occasions when it might be greater than 1. It might just because of a poorly designed question on my part. But generally, the coefficient of friction is less than 1. Okay, so we are to find the object's acceleration. Let's draw a free body diagram. Let's start with that. Free body diagram. So we got our little box thingy. It's got a mass of 10 kilograms. I quite often just put the mass inside. We got 100 newtons applied to it. Doesn't tell us what direction. We'll assume right. We live in a left to right society. Generally here in North America. Come on, FA. Loud. Okay, so I got that is the applied force. Let's see if I can draw that better again. FA, there we go. Okay, there's 100 newtons applied to it. The coefficient is 0.25. Determine the object's acceleration. So we do have some friction force here, but we're not sure what it is. Is there a weight force and a normal force? Absolutely there is. But because they're flat, the object is flat, would you say that the weight force and the normal force are equal to each other? Yes. They are, right? Otherwise, the object would be jumping up in the air, falling through the floor, right? Okay. So the net force up and down is balanced. Do we need to know the weight force? I know the mass. Eventually, I'm going to have object acceleration. I'm going to have net force, F net is equal to ma, right? So I got to get my a. I know my mass. Right? But I need my net force. Do I need the weight force? Doesn't hurt. Let's do it to begin with. Pretty much always you're going to need it at some point, right? So let's just get it out of the way. So that's going to be mass times gravity, mg, 10 times 9.8. Nate's going to ask if it's negative. No. Come on, go ahead and ask.
Doesn't matter.
Does it not matter in this case? I don't think it does. But it's not going to hurt to make it negative. Because we can say that, no, apparently I can't do the math in my head there. Hey, I recognized. There we go, minus 98. Minus 98 down. Which means, therefore, 3 dots, therefore, my normal force up is going to be 98, exactly. Positive, right? Okay, good. I feel shame. Okay. I can't get my net force until I get my friction force. So what am I going to do? There's a brand new one. Mu equals FF over Fn, because I now have my Fn. I now have my Fn, and I know my mu value. 0.25, was it? And this is going to tell me my friction force, FF. Fn is this 98. Yeah, multiply. FF equals 49. Half of 49 is going to be 24.5. .5 is my friction force. You know how I did that? I took 98 and divided by 2, which I know was 49, and then took that, I could divide by 2. I know. Genius. Okay, net force. Just to differentiate here, I'll go a different color. Not yet, Nate. Yes, got to do all the forces added. So F net. Notice that I put plus FF there. No, you go right ahead. That say, what about FW? Go ahead, say it. Say, what about FW? Yes, technically you're not incorrect. But having said that, plus the weight force plus the normal force, we already know that they cancel out, right? They're up and down. Do they have any bearing on the net force now? No. So most people will just ignore them. But you're not wrong, Nate, when you say that. Okay? Okay, so my applied force is, what was it, 100? Notice that I've got plus FF, because we're really just doing vector addition. We're adding up all the forces. So it's this 24.5 is actually negative. Now notice that it doesn't come out negative. So you just have to make it negative because it's to the left. Yes, it's your job to assign that negative because it's left. You're going to get 124.5 and it's going to be wrong. Right? You will definitely lose a half mark there. Yeah. That's right. Never. Well, that's not true. If you do it better the next time, I'll probably make a change. But definitely a common mistake. So don't do that. Let's see if I can do this in my head. This is going to be 75.5 newtons is my net force. And I definitely need more room on this page. Now I can find my acceleration. F net is equal to MA. 75.5. I sure wish they didn't put this thing so low. What's the mass? 10? .5 divided by 10 equals 7.35 meters per second squared. Where did I get 3 from? Yeah, what am I doing? What am I doing? Somehow I turned 75 into 73.
7.55.
Yep, go to the bullpen. Bring in the lefty. Yeah, oh, I'm having a tough start on the mound. If only life could be like that, right? I'm having a tough day. Let's go to the bullpen. Go to the bullpen. You know, Saturday Night Live could be a lot funnier if they just took some of my ideas. Yeah, I think so. Maybe they could have like politicians in the bullpen too, right? What would the politicians be doing in the bullpen to warm up? Yeah, practicing their lies. That's funny. Okay, let's look at example 2. Yep, ramps. We can do it, Nate. We can do it. Object has a mass of 10 kilograms. We'll leave it at 10 to make it easy. It's placed on a ramp with an angle of 35 degrees. The coefficient of friction is 0.15. Determine the object acceleration down the ramp. Now remember, yesterday I said if there's no friction, acceleration is g sine theta. We got friction. It's going to be less than g sine theta. Let's start with our picture. FD, right? From yesterday. Which way is the friction? Up the ramp. Exactly, Will. So really, I guess, like, what's different from today from yesterday, right? We're just going to do the same things, except we're going to subtract friction. Really, just like we did here, right? The only difference is it's on a ramp. Okay. Do we need the weight force? Yeah. Well, eventually. Although you will remember from yesterday that FD, force down the ramp, is actually mg sine theta. If I did the weight force, I could just substitute it in there, but I'm not ever going to actually need the weight force. Like, I'm always going to use a part of it, right? So I don't actually need it. If you find it, it's not a big deal, because it's really just that mg. So we're going to have 10, 9.8 times, whoops, because of this triangle here, right? And this FD here is opposite the angle up here. Well, I went through that yesterday, man. The formula is FD is mg sine theta.
Wait, FD is always sine?
Always sine.
Okay.
Always. Oh, okay.
Well, it's in the middle. It's coming off and plopped in.
10 times 9.8 times sine 35. I didn't even bring a calculator today. Holy moly.
You are the calculator.
Well, I don't have the trig tables memorized. You know, I did back in my prime. What is it? 56.2? I'll take your word for it, Cole. 56.2 newtons. I'm going to put my units there. That's down the ramp, right? Okay. How do I find friction force? Well, how did I find the friction force on this previous one? I use this, right? U equals FF over Fn. I don't have my Fn yet. I got to do that. On the flat surface, it's equal to Fw, but it's not a flat surface. So on a ramp, yesterday you learned that Fn is equal to mg cos theta, which is just mg, weight force, times cos theta, right? Because the ramp changes the value. Getting understand what's happening? Yeah? Okay, so that's going to be mass of 10, 9.8, sine cos 35, 98 times cos 35, 80.3? Oh. 80.3. Okay, but that's just normal force, right? Nate, pretend it's Remembrance Day for me. We're right at that part where there's the moment of silence. But, like, do it back to back for about 25 times. Mu equals FF over Fn. What's the mu value here, Nate? 15 this time. FF is what we're solving for. Fn is this 80.3 that we just calculated, 80.3, giving me friction force FF. Cole, I'm going to have to rely on your calculator abilities again. 12.045. What's different about this from the previous one? Well, here I found weight force to get normal force, right? So instead of doing this, I'm going Fn is mg cos theta, but I'm still finding my friction force using mu. Next step is going to be F net is equal to Fa plus Ff, but is there an applied force in this one? No. There isn't. But what's causing it to slide down the ramp? Fd. So my Fd is kind of like the applied force. So, yeah. So, because it's opposite friction, that's good. Now, you'll notice again, friction doesn't come out negative here, right? So you're going to have to assign it to be negative. F net applied, oh, not FA. FD plus FF. 56.2. Hold that thought. 46. 44.2 newtons, right? Okay. So that's the net force down the ramp. Now the question is, does the normal force cancel out with the weight force? And the answer is no. But we've taken care of that because the FD, right, exists because it's sort of the difference between. Does that make sense? Like the FD is there because there's a difference. That's a really good question. I don't think I've ever actually had anyone ask me that before. I had to sort of stop and think how I'm going to. That's why I said, give me a minute. I had to think about how I'm going to explain it. Yeah. The FD is the difference, and I'll use air quotations, between the normal force and the weight force. That's good. Awesome. Okay, so now I got my net force, and now it's pretty easy matter. F net is equal to MA. 44.2 mass is 10. See if I can do this. 4.42 meters per second squared. And if you had to find out how fast it's going or something like that, you could do that at the bottom of the ramp. Okay, so two very similar questions, just one on a ramp, one flat. And I hope you can see the differences. Good, Mustafa? You know I can see right under the table. You're not doing a very good job of hiding it, yeah. Yeah. We could split it into two, but you're gone before then anyways, so yeah. Let me do some thinking tonight and some calculating. Yes, will do. Okay. Okay. This example is a little different here. A box weighing 40 kilograms is pushed along a level floor at a constant speed by a rope that makes an angle of 30 degrees with the floor as shown. I don't have the picture yet. If the force on the rope is 260, what is the horizontal component? What's the normal force? What is the coefficient of sliding friction? This is a challenge question. Okay? Notice that it clearly says a level floor. Okay? I've noticed in grade 11, people have a hard time differentiating between questions where it's on a level floor and the force is at an angle, or it's on a ramp, because they're kind of similar, right? But you got to make sure you know the difference. This is which one? This is level floor, like this, right? So it's a 40 kilogram box. Yeah. It's 30 degrees right here. The force on the rope is 260. What is the horizontal component? What's the normal force? And what's the, this time we're asking for the mu value. Is the fact that it's moving at a constant speed important? It means no acceleration, which means no net force, which means that forces are balanced or equal, exactly. So we actually have here, we're going to have a horizontal component, just like we did components of vectors, x and y. I like to call it FH. Mr. Smigalski likes to call it FX. Maybe I should do that. I'm going to do that. I'm going to call it FX. FAX, I think he calls it, right? Yes, I think that's what I saw in grade 11 when I was away. I think he called it FAX. This would be FAY. I might slip up, so correct me if I slip into my old habits. FAX, horizontal component, X component of applied force, Y vertical component of FAY, of applied force. Is there any friction here, Josh? It doesn't say frictionless, and it's asking for coefficient of sliding friction, so yes. 30 degrees probably. Really lousy 30 degrees. Which way is friction? Friction is back like that, right? And again, all these forces are balanced. Oh, we've also got a weight force, FW. Do we have a normal force? Is the normal force balanced by the weight force? I sort of didn't give you all the truth last time. I'm so emotional, I got a voice crack there. Okay, I sort of didn't tell you the whole truth. Because of what? Because this FAY is here, it's also in the direction of the normal force. So we're going to get to that right away. Okay. Let's look at part A, which is horizontal component, FAX. Now, FAX is going to equal, Nate, concentrate, man. The FAX is adjacent to the angle, so it's going to be FA cos theta. It's going to be the cosine. How much is my applied force? 260. Cosine theta, cos 30. 260 cos 30. Well, it's going to be less than 260. 225. 0.2. Okay, 225.2. So that's how much is actually pulling it sideways, right? That's how much is pulling it sideways. Eventually, I've got to come up with mu. Mu is FF over Fn, right? So I'm not anywhere close yet. I got to come up with FF, and I got to come up with Fn. How much is the FF? How many forces are moving to the right? Just the FAX is moving to the right. How many forces are moving to the left? Just the FF. So Josh, how much is FF? Actually negative. How come negative? I didn't say it was a no-brainer, did I? Constant speed. It's because it's at a constant speed. Therefore, FF is minus 225.2. How come? Because it's moving at a constant speed, all of the forces must be balanced. The acceleration is 0, the net force is 0, the force must be balanced. All the x forces must be balanced, all the y forces must be balanced. So the FAX and the FF are the only x forces, so they are equal and opposite. So we're one step, right? What's the normal force? Same principle. The normal force is up, the weight forces down. Usually they're the only ones, but this time there's this FAY here. So we have to be very careful with our signs here. Do we need the numerical value of FW? We sure do. Mass times gravity. 10. Now, Nate, does the negative matter here?
Yes, sir.
Why do you say yes? And you're right, by the way. Well, because there's up and down, and we also know that this FAY is part of it, so it's not balanced. It's not just sort of a throwaway who cares thing. It's actually important. So, minus 98. What was it? Oh, it's 40? Okay, that's too bad. Because I know I can't do it in my head. What would it have been? 98, 392. That sounds familiar. Thanks, Will. 392 newtons, and that is down. Negative 392. Down. How much is the FAY? Up.
Isn't it?
We don't know yet. The opposite to the FAX. Exactly, Nate. Well done. Well done. Oh. FAY is going to be FA sine theta 260 sine 30 how much? 130? In which direction, Josh? Up, so it's positive. Now there's various ways that we can write this next step, and I think I'm going to select a different way because it's kind of the way I've been talking about it all along here. Would you agree that the net Y forces, the up and down forces, are 0? Right? It's not moving up or down, is it, right? It's moving sideways. So the net forces up and down, in fact, the net forces X are 0 as well, right? So I'm going to write F net Y. The net Y forces are 0. And what makes up the net Y forces? FW, Fn, and FAY. Does it not? Those are the three that are up and down. So now plug in your values. Careful with your signs. So the FW we said was minus 392. The normal force is what we need eventually. And the FAY is up at 130. So really, the FAY is sort of helping the normal force. That's a plus 130. Oh, right here, plus Fn stuff. And it's all equal to 0, right? Because the net Y forces are 0. It's not going up or down. It's not accelerating up or down. So the 392 is going to go to the other side and become positive. The 130 is going to go to the other side and become negative. And you're going to have 392 minus 130. That is my normal force. That's equal to it. Fn is 262, right? That I can do that subtraction in my head? Here's how I did it, Nate. 2 minus 0, 2, 9 minus 3, 3 minus 1. That's called arithmetic. They used to make us do that in the good old days. Okay, now I've got mu equals FF over Fn. Friction force from way up here, minus 225. Does it have to be minus? Mu doesn't care, right? There's no direction to mu. Mu doesn't care about what direction. Is it going to be less than 1? Yep. That should make you feel good because that's where it should be. If it was greater than 1, check your work. It's unlikely.
What if you messed up?
Well, that's certainly possible. I've messed up many times before. How much? 0.86. Any unit? No units. How much would I give you? How much would a question like that be worth, you think, all told? Well, 1 for that there. 1 for this. 2. 3. 4. Yeah, 5. 1 more for the picture? Okay, if I'm generous. Alrighty, I am done. I've had enough talking. What time is it? Oh, we are very close to done. You now have, I need to give you this. You guys out there should have another handout. I think it came as 2 separate ones. It just says friction questions. There are 10 questions here. There are some problems. There are 11 problems. There are answers attached. You have plenty of stuff to work on. I think it's time I gave you a period just to work. I'll actually good. I'll answer that right away, Nate. So plan for tomorrow to be a bit of a work period. Thursday, maybe. I know there's a couple of you guys are away on Thursday. We'll see how that goes. Nate is asking about, in the first handout, the one with the words, he's asking about the table of values on the bottom, right? On page, bottom of page 3. There might be the odd problem where it doesn't give you a coefficient of friction. It will likely be on that table, that's all. Okay? Yeah, so like you'll see like steel on steel, it starts at 0.74. Glass on glass is 0.94. Yeah, they're not there, I don't know. Yeah. Those are just examples, really, so. Okay, I'm done yakking.